Hello viewers, as I am uploading the videos of complex analysis, in the previous video I uploaded about complex integration and line integration and a few examples based on that. In this video I would like to discuss Cauchy's integral theorem and Cauchy's integral formula and derivatives of an analytic function. So let's see what is Cauchy's integral theorem. Its statement is that if a function fz is analytic and its derivative f dash z is continuous at all points inside and on a simple closed curve C, then we have that closed integral C fz dz is equal to 0. This we have to prove. So let's see what is or how we can prove this. So we know that integral C fz dz, this is closed integral, is equal to u dx minus v dy plus I v dx plus u dy under integral sign. This we have seen in the previous videos, because when we write fz in terms of u plus iv and dz as dx plus I dy, so when we separate real and imaginary parts we get these terms, and we got two terms here. So this is the first term and this is the second, which is an imaginary part. Now we know that fz is analytic and its derivative exists. It means partial derivatives of u and v, because fz is equal to u plus iv. They are continuous. Partial derivatives of u and v are continuous. And then by Green's theorem, what is the statement of Green's theorem? Let's see. This is this where we have this expression that u dx plus v dy is equal to, this means line integral has been converted into double integral, curve has been converted into region. So in the first term, if we see that v is with minus sign, here it is with plus sign, so wherever v is there we will take it with minus sign. So first term on right hand side will be minus del v over del x. So our first term will be double integral r minus del v over del x minus del u over del y dx dy. So this is the first term. In the second term we see that we have v dx plus u dy, means our coefficients have been exchanged. Here with the dx it was u and with dy it was v, but if we substitute in place of u as v and in place of v as u, then we can write this term which is on right side. So in place of v we have written u, we got del u over del x minus del v over del y dx dy. So we got these two terms with the help of Green's theorem. Now we use Cauchy-Riemann equations and we see that both the terms becomes 0, they cancel out when we use CR equations. So our proof is over that integral C fz dz is equal to 0. So we have a corollary here. Next, if fz is analytic in D and if 2 points A and B joined in D, D is a domain by two different curves C1 and C2 lying wholly in D, then we can first see the figure and then we can use the Cauchy's integral theorem. So here A, B are, these are the 2 points. A, D, B, E, A is the closed curve. This is anti-clockwise, and we can write down with the help of Cauchy's integral theorem that integral fz dz is equal to 0 over the curve A, D, B, E, F. This is the closed curve. This is equal to basically summations of two line integrals, that fz dz over A, D, B and B, E, A. So we can change the order of this B, E, A and we can take it clockwise direction with minus sign. So this becomes fz adb minus aeb fz this. So both of them, they are cancelled out and this is equal to 0. So we can write down integral fz dz over c1 is equal to integral what path that you take so long as the endpoints are same, provided fz is analytic between any of the two paths. This we have seen in our previous videos also, when we proved that function is analytic or not, or when we calculated the integral value, evaluated the integral value. If fz is not analytic at some point between two paths, then the path does matter. This happens in our real calculus. One example here, that it says integrate w is equal to fz is equal to 1 upon z. Function is given to us which is 1 upon z. Over the curve is given unit circle, that is z is equal to e to the power I theta, and theta is from 0 to 2 pi. So we see the unit circle, this is z is equal to e to the power I theta is unit circle, where this is real of z and this is imaginary of z. R is equal to 1, angle is, so whenever our pi circle or unit circle problem, we use the polar coordinates. So we write down 1 upon z as r e to the power I theta. R is given 1 because it is given z is equal to e to the power I theta. So this is e to the power minus I theta. So dz is r e to the power I theta, r is 1. So when we differentiate it, we get I e to the power theta d theta, and we substitute in our integral, which is fz dz. So curve is 0 to 2 pi, that is unit circle circumference whole, so it starts from 0 and come back to 0, that is it rotated 2 pi angles. So e to the power minus I theta, I e to I e I theta d theta, this is the value of dz, and this is our 1 upon z when r is 1. So when we simplify, we get 0 to 2 pi d theta, because e to the power minus I theta, e to the power I theta cancelled out, I is common. When we integrate, it comes 2 pi I, and it is not 0, though it is closed curve, because if we see the Cauchy's integral theorem, it should be 0, but it is 1 upon z, so it is discontinuous, singularity is there, and therefore, and this singularity is a pole at z is equal to 0, therefore the integral value is not 0 here. In this example, we evaluate 1 upon z minus 2 over the curve C, which is a unit circle, so mod z is equal to 1, and fz is 1 upon z minus 2. It means it is not analytic at z is equal to 2, and we have the domain as mod z is equal to 1. It means this point, that is z is equal to 2, lies outside the domain. It is a singularity which lies outside. So we can say that inside we can apply Cauchy's theorem, and integral c dz upon z minus 2 is equal to 0. Now let's take another where fz is same, but mod z is equal to 3 means size of domain has been increased. So now this singularity lies inside the curve, and then we have to apply the integral, which we have seen in corollary, and with the help of corollary we can get the integral value as 2 pi I. Now let's see multiple connected reasons. A simple curve is one which does not intersect itself. So a circle is a simple curve, this figure is a simple curve, and if curve crosses itself, then it is not a simple curve, and this curve is crossing itself. Two loops are being made. So simply connected domain is a domain D in the complex plane such that every simple closed contour in D encloses only the points of D. If the domain which is not simply connected is multiply connected, so this figure is multiply connected where we have two loops, and now we see further figures. So doubly connected figure is this one, where we have two circle shaped, not exactly circle but oval shaped figures, and this is triply connected. One part is this part, another is this part, and third is this part. So this is triply, so we can have multiple connected multi-connected region can be converted into simple connected by giving one or more cuts. So this is doubly connected region. We have two curves which are, this is anti-clockwise and this is clockwise. So anti-clockwise and clockwise. Now we give one cut to this, and cut is from A to B. So we can now write down by Cauchy's integral theorem that integral CFZ dz is equal to 0, and it is, now we take the path A to B, then we took C1, then BA, and then C2. This is C2 is equal to 0. So this way we can convert it into simply connected. C1 and C2 have been taken in anti-clockwise direction. So we can write down integral fz dz C1 is equal to integral fz dz C2, because AB and BA will be cancelled out. So these two terms will be cancelled out, and when we take C1 and C2, their directions are opposite, so with minus sign we'll go on right hand side and we will have this expression. Now let's see Cauchy's integral formula and its proof. And the statement is, if the function fz is analytic within and on a closed curve C, and z0 is any point within C, then the statement that integral C fz upon z minus z0 dz is equal to 2 pi I f z0. Here we see that fz is analytic, but at a point z0 it is not. There some singularity exists. So let's see how to prove it. We have a function that fz upon z minus z0. So as I said, at z is equal to 0, at z is equal to z0, it is not analytic. So what we do, we draw a small circle enclosing the point z0, and we call that circle as C1, and radius of that circle is rho. So we took it clockwise direction, and then the function is analytic in the region enclosed by C and C1. So C1 lies inside C. And now we use Cauchy's. So now we have two contours C and C1, and we write down integration over both, and these are the two terms we get. Now we write down the circle equation, that is z minus z0 is equal to rho e to the power I theta. Rho we have taken radius of the circle around z0. z0 is the center of the circle and angle is 0 to 2 pi. We can write down dz value. Dz is I rho e to the power I theta d theta. We substitute these in the integral. So first term is same, and in second we write down this term where denominator and numerator rho e to the power I theta, they cancelled out, and I we take common and we write down these term. So these two terms are there. Now for any value of rho it is 2, the second part is 2, so we take rho tends to 0, and when we take rho tends to 0 we write rho as 0 in the second term, and we get this I integral C1 fz0 d theta is equal to 0. We got these two terms, and when we calculate the second term, fz0 is not depending on theta, so inside the integral of C1 only d theta is there. Angle is 0 to 2 pi, but it is clockwise. C1 is clockwise, so when we take the limit it's 2 pi to 0, so we have reversed the limits, which gives us minus sign here, and first term is same and second is minus 2 pi I fz0, and this is corollary of Cauchy's integral theorem, and we get integral c fz upon z minus z0 dz is 2 pi fz0. So this is our Cauchy's integral formula. Now we can see one example based on it, and this is the example where C is a circle with center 0, radius 2. So it is having the singularity at z is equal to minus 1, and it is lying inside the domain. So here fz is e to the power minus z. So we have basically fz is e to the power minus z, z minus z0. Minus z0 is here minus 1, means z0 is minus 1. So we can write down this as 2 to the 2 pi I e fz. 2 pi fz is 2 pi I e to the power minus z, and where it is z is equal to minus 1. So when we put z is minus 1, we get this value. And we have second where z minus 5 is equal to 2. So here our center is minus 5 and radius is 2. So this minus 5 is the center and 2 is the radius. So singularity, that is z is equal to minus 1, is lying outside the domain. So this becomes 0, integral becomes 0. Now derivative of an analytic function at z0. If fz is analytic inside and on a simple closed curve C, and z0 be a point inside C, then all the derivatives of fz exist at the point z0 and are given by the formula. So this is the formula, and we have the first derivative is this, nth derivative we can write down by this formula, and based on this we can write down one example, that if e minus z, z plus 1 square, and of course it is over the curve C where mod z is equal to 2. So by using formula we can write down this value, and this is the answer of this problem. Thank you.